I'll start presenting. In the last lecture, we have started with single phase full wave fully controlled rectifier with R load for center tap configuration with R load, RL load and freewheeling diode. I think we have covered all these three variations of the load for single phase full wave controlled rectifier uh, center tap configuration. Can you see this screen? Hello.
Yes, sir.
Okay. So now we'll start with single phase full wave control rectifier bridge configuration for all three load variations: low resistive load, then resistance inductance combination, and resistance inductance plus the freewheeling diode. This is the circuit diagram for single phase full wave control rectifier bridge configuration with resistive load. For the simplicity, we should not show this voltmeter and this gate pulse, right? We should avoid this because it will create confusion. And this is not only the thing. We have to show, if you want to show the gate pulses, we have to show the gate triggering circuits also. So to avoid the confusions, we should not show this pulse waveforms or this voltmeter, etc. For that, we need to show this type of. Hello.
सर कोणी स्टुडंट्स आलेत का ऍक्सेप्ट करायला ऑप्शन तिकडे?
नाही दिसत आहे रे, सगळ्यांचं ऍक्सेप्ट केलंय.
अच्छा अच्छा, ठीक आहे ना सर.
30 स्टुडंट्स आहेत टोटल.
अच्छा अच्छा.
दुसरी स्क्रीन दाखवायची, ती स्क्रीनच शेअर नाही होत आहे.
सर फुल विजिबल करा ना स्क्रीन मध्ये.
एंटायर स्क्रीन का?
हा, फुल करा, मग त्याने सगळं होत. त्याने कधी एरर नाही येत मग.
नाही दिसत आहे ना रे, चेक करतो थांब. ठीक आहे, याच्यामध्ये पण आहे ना. दिसते सर्किट, सिंगल फेज फुल वेव कंट्रोल रेक्टिफायर विथ आर लोड.
हा सर,
दिसते ना याच्यामध्ये. बघा, आपण याच्यामध्ये गेट पल्सेस नाही दाखवले, कुठलं व्होल्ट मीटर पण नाही दाखवलेलं. राईट. दिस इज द सिंगल फेज full wave control rectifier bridge configuration. Simple resistive load is connected, and as it is full wave control rectifier bridge configuration, we require 4 switching devices, and all the 4 switching devices are SCRs, because we are studying this single phase full wave fully controlled rectifier. To be very precise, it is called as fully controlled rectifier. So what should be the title of this circuit? You can note it down: single phase full wave fully controlled bridge configuration with resistive load. Right. Now this on the input side there is AC supply, which is connected to 230 volt 50 volts AC, and there can be a transformer, secondary, primary, and etc. that we need not show in bridge circuits. But in center tap, we have to show the input side transformer and the AC supply. Here in bridge configurations, we are not showing any input side, just we are showing 2 terminals where AC supply is connected, that's all. So this VS indicates AC supply, it is not DC as it is shown as plus minus. This is just assumption that during positive half cycle, upper terminal is positive, lower terminal is negative. That's it. It is not a DC supply. Please remember, this is AC source. Why plus minus is shown? It is assumed that it is a positive half cycle, right? So input side only, just you can connect these 2 terminals and they draw a circle in between and show a AC sign. AC का साइन जो रहता है साइनोसाइडल वेवफॉर्म, that also will work. Instead of showing this plus minus, जिनको समझ में आता है वो लोग समझेंगे कि ये AC सप्लाई है, लेकिन इसने टर्मिनल्स दिखाया है. But someone may also assume that he has shown as DC source, and that he will assume that it is a wrong. So instead of doing this, you can draw a circle in between these two and show a AC sign. That will be better option. So on the input, there is AC. This circuit consists of 4 switching devices. All are SCRs, because it is a fully controlled rectifier circuit, and it consists of a resistive load. Clear? And on the waveforms below this AC sine wave, you need to draw the gate pulses for first one is IG1 and IG4. Same gate pulse is applied to SCR1 and SCR4. So in first waveform, you should show IG1 and IG4, and in second, you should show IG2 and IG3. So 2 SCRs are conducting simultaneously. The pair is in first half cycle, SCR1 and SCR4 will conduct and in second half cycle, that is negative half cycle, SCR2 and SCR3 will conduct. That's why we need to show the gate pulses for SCR1 and SCR4 together at an angle alpha. Here you can show a gate pulse which is applied to SCR1 and SCR4. Here you can show here gate pulse is applied to a pair of SCRs, SCR, uh, this type of waveforms you need to show. It is called as IG1 and IG4. Similarly, below this you can draw the waveform for IG2 and IG3. So this is IG1 and IG4. So below this you can draw यहाँ पे at this point IG2 and IG3. So first of all, you need to draw this AC input, then this IG1 and IG4, then this IG2 and IG3. And after that, you can draw output voltage, then output current or currents through SCR1, SCR2, SCR3, SCR4, etc. and load current and voltage across SCRs. Now the working of this circuit, as soon as AC is applied to the gate, SCR1 and SCR4 will be forward biased. Why? Because the anode of the SCR1 is at highest potential, that is positive, and the cathode of SCR4 is at negative maximum potential. So this is forward biased and this is also forward biased. So pair of SCRs 1 and 4 are forward biased during positive half cycle, and as we apply the gate pulse to SCR1 and SCR4 at the same point, simultaneously we are applying the gate pulses to SCRs 1 and 4 at an angle omega t is equal to alpha. So as they are forward biased and a gate pulse is applied to their gate, they can start conducting. They will be triggered. SCR1 and SCR4 will be triggered at an angle omega t is equal to alpha, and the current starts flowing through the circuit as shown. It will start from the positive of this wire, this terminal, as it is positive of cycle, it is positive terminal, then it will go to SCR1 as it is forward biased and conducting, then it will go to load this way. I0 is flowing through the load, and then to SCR4 and back to the negative of the source. So this way the load current flows through the circuit during positive half cycle, right? And this is the load current waveform. You are going to get the load current from omega t is equal to alpha to omega t is equal to pi. And at omega t is equal to pi, this SCR1 and SCR4 will be reverse biased by natural commutation. It will be turned off. As the voltage polarities are automatically reversed at omega t is equal to pi, this terminal becomes negative, this terminal becomes positive. Therefore, SCR1 and SCR4 are reverse biased and the load current goes to zero. Therefore, both the conditions required to turn off the SCR are satisfied. Condition number one is the voltage across the device must be reverse biased and the current flowing through the device must be less than the holding current value. Here, the load current is zero and the voltage polarities are reversed. Therefore, pair of SCR which was conducting, that is SCR1 and SCR4, will turn off at omega t is equal to pi, and there is no load current because there is no conducting device from pi to pi plus alpha. The load current as well as the load voltage both are zero from omega t is equal to pi to omega t is equal to pi plus alpha. Now we are going to get the output voltage from alpha to pi when SCR1 and SCR4 is conducting. Similarly, we are going to get the load current from alpha to pi when the pair of SCR1 and 4 is conducting. From pi to pi plus alpha, there is no load voltage, no load current. What about voltage across SCR1? From 0 to alpha, as the SCR1 and SCR4 are not conducting, so it will block the voltage applied across it. Therefore, the voltage across the SCR is positive spike here. That is the nature or the shape of the input voltage. यहाँ तक ये voltage SCR ने block किया है, SCR1 ने, and at omega t is equal to alpha, it is conducting. Therefore, the voltage across the SCR is 0 from alpha to pi, and from pi to pi plus alpha or 2 pi plus alpha, the voltage across the SCR1 is voltage appearing across it, that is the input voltage negative, and from this it will appear positive. ये shape जो है input का वही shape लेगा, right? This is voltage across SCR1. बाकी you can draw voltage across SCR4. It will be opposite of this because opposite polarity voltages are applied across SCR1 and SCR4. Here cathode of SCR4 is connected to negative terminal. That means it is at highest negative potential. That's why it is forward biased. Now the currents flowing through the SCRs 1 and 4 is similar to the load current during positive half cycle. Positive half cycle में जो current flow रहा है, that is the same as the current flowing through SCR1 and SCR4. Now at omega t is equal to pi plus alpha, we are applying the gate pulse to the SCRs 2 and 3. During negative half cycle, SCR2 and SCR3 are forward biased because the anode of SCR2 is at highest potential and the cathode of SCR3 is at highest negative potential. That means these two SCRs are forward biased. As we apply the gate pulse at omega t is equal to pi plus alpha, this is at omega t is equal to pi plus alpha. It is applied to SCR2 and 3, and SCR2 and 3 starts conducting. The flow of current will be from this terminal. Now this is positive terminal. During negative half cycle, this terminal is positive. So the current flows through the pair. It will start from this point, goes to SCR2, then load, and through load it comes back here, and through SCR3 it goes to the other terminal of the supply, that is negative. So in this way the current flows through the circuit through SCR2 and SCR3, and we'll get the load current and load voltage across the load. So this is the load voltage when SCR3 and SCR2 are conducting. This is the load current when SCR3 and SCR2 is conducting. Both are same because the load is resistive, and this is the current flowing through IT3 and IT4. SCR3 and SCR4 when they are conducting. It is very similar to the load current when they are conducting. Load current and the current flowing through the SCR2 and SCR3 during negative half cycle are same. I think this is clear to all how the circuit works. And at omega t is equal to 2 pi, the SCRs which were conducting, that is SCR2 and SCR3 will turn off by natural commutation. यहाँ पे दोनों SCR turn off हो जाएंगे, और from 2 pi to 2 pi plus alpha there is no conducting device, so the voltage across the load is 0 and the current flowing through the devices or circuit is 0 from 2 pi to 2 pi plus alpha. And again at 2 pi plus alpha we are applying the gate pulse to SCRs 1 and 4 यहाँ पे, or as they are in forward bias they will start conducting and we will get the load voltage current from 2 pi plus alpha to 3 pi. So cycles repeats one after another after pi degree angle, that is 180 degrees. I hope this is clear to all how the circuit works. Is there any doubt?
No, sir.
Clear na?
Yes, sir.
It is very easy. So there can be a question like explain the working of single phase full wave bridge configuration controlled rectifier with resistive load. Draw a circuit diagram waveform, and you need to derive the equation for the output voltage also. So if such type of question is asked, then you need to draw this circuit diagram and these waveforms and explain the working of the circuit, and you need to derive the equation for the output voltage or average DC voltage or average load voltage. ये V0 है ना, इसके लिए आपको voltage equation derive करना पड़ेगा. The average voltage will be इसका एवरेज रहेगा. That depends on the value of the firing angle. This can come down or go up. If the firing angle alpha is increased, that is more firing angle, you will get lower output voltage. If firing angle is less, you will get more output voltage. So it depends on the angle at which you are triggering the SCRs, and the voltage will be average of this. 1, 2, 3 जो भी pulses मिल रहे हैं उसका average will be the output voltage. How will you derive this equation for average output voltage? First of all, do you think there is any difference between this circuit and the circuit with circuit of center tapped full wave control rectifier? वेवफॉर्म में कुछ डिफरेंस है? Center tap configuration with same load and bridge configuration with same load, that is resistive load. Is there any difference in the waveforms? There is no any difference, because that is also full wave rectifier, this is also full wave rectifier. The difference is only at a time in center tap only one SCR is conducting, whereas in bridge configuration at a time there are two SCRs conducting. The output voltage waveform is very similar. Therefore, the output voltage equation must also be similar. That is, V0 is equal to Vm by pi into 1 plus cos alpha. How you will derive this? V0 is equal to 1 by pi integration from alpha to pi Vm sin omega t d omega t. And after simplifying this integration from alpha to pi Vm sin omega t d omega t, you will get the average output voltage equation as V0 is equal to Vm by pi into 1 plus cos alpha. It is very similar to the circuit with center tap configuration. Now, can you see this other circuit? कौन सा सर्किट दिखाई दे रहा है अभी आपको?
इंडक्टिव लोड वाला.
इंडक्टिव लोड वाला ना? Okay, that means I have to change this presentation. Okay, so this and that circuit is same, only यहाँ पे थोड़ा complications बढ़ा है इन लोगों ने. यहाँ पे वोल्ट मीटर दिखाया है. ये देखो, ऐसे एक सप्लाई दिखाओगे तो काम चल जाएगा. इनपुट साइड में एक दो लाइन ड्रॉ करके वहां पे बीच में सर्किल ड्रॉ करके एक एसी का सिंबल दिखाओ. ये इतना सब करने की जरूरत नहीं है. ये दो टर्मिनल्स है, इसके बीच में सर्किल ये ड्रॉ करके ये करो, बस हो गया. और ये वोल्ट मीटर, ये ट्रिगर पल्स, ये सब दिखाने की जरूरत नहीं है. Okay, this is the equation for output voltage. VDC is equal to 1 by pi alpha to pi Vm sin omega t d of omega t, which is equal to Vm by pi minus cos pi minus of minus cos alpha. After simplification, you will get Vm by pi into 1 plus cos alpha. So the average output voltage VDC depends on the value of the alpha. As you go on increasing the value of alpha, your output voltage will decrease, and if we decrease this alpha, EDC will increase. So depending on the alpha, the output voltage can be varied. That's why it is called as control rectifier. We can control the output voltage by controlling the trigger angle or firing angle or phase angle. You should note down this output voltage equation, otherwise you will get confused. There are so many control rectifier circuits. There are various loads, various configurations, single phase, three phase, half wave, full wave, R load, RL load, freewheeling diode. So many things are there. For every configuration, you need to have the output voltage equation formula. So please remember all these formulas for different configurations and how it is derived. This is simple step. Within 3 steps, you will get the average output voltage equation. And if you write directly this, you will get some less marks because they have asked to derive. Derive means कहाँ से शुरू हो गया, इनपुट कैसे अप्लाई किया, कहाँ से कहाँ तक आउटपुट मिल रहा है आपको, और फाइनल इक्वेशन क्या है. That is called as derivation. Derive the equation. You cannot directly write down this output voltage equation. Derive it by taking this integration, and 2-3 marks will be added in your total. Otherwise, if you write it directly, 2-3 marks will be reduced. Then this is normalized voltage. Vn is equal to Vdc by Vdm 0.5 cos alpha, that is 50%. And the RMS voltage Vrms is equal to under root of 1 by pi integration from alpha to pi Vm sine of omega t whole square d of omega t, which is equal to Vm by under root of 2 pi square root of pi minus alpha plus sine 2 alpha by 2. This equation is also important. अभी कौन सा स्क्रीन दिखाई दे रहा है? With an inductive load, RL load.
हाँ, इंडक्टिव लोड. इंडक्टिव लोड सर.
अभी चेंज हो रहा है क्या? देखो, स्लाइड चेंज हो गया?
नहीं.
नहीं ना? हाँ, ठीक है. अभी दिखाई दे रहा है? With an inductive RL load.
हाँ सर.
हाँ. The next circuit is single phase full wave fully controlled bridge configuration with RL load. Note it down. Single phase full wave fully controlled bridge configuration with RL load. This is the title of this circuit. What is the difference between previous circuit and this circuit? इसके पहले वाला सर्किट कौन सा था? No answers.
रेजिस्टिव लोड सर.
The difference is only this inductance is added in this, whereas it was not there in previous circuit. It was only consisting of pure resistive load. And here it is assumed that the inductor is of low value. Assume करा है. RL load and inductance is of low value. Why? Because I'll explain the reason. यहाँ पे देखो ये waveform. ये देखो यहाँ पे 0 पे गया है लोड वोल्टेज, और 0 पे जाके वहां पे 0 ही रह गया. कहाँ से? बीटा टू अल्फा. During beta to alpha there is no load voltage. It is discontinuous because the inductor value is low. If the inductor value is large, ये ऐसे रहता था continuous negative. यहाँ पे दिखा है, next इसमें देखेंगे. ये देखो, है ना, continuous negative, then ये positive हो गया. There is no zero ड्यूरेशन. जीरो वोल्टेज होता ही नहीं, यहाँ से तो पॉजिटिव है या फिर नेगेटिव है. If the value of the inductor is very large as compared to the resistance, यहाँ पे value of the inductor is low, that's why we are getting the zero voltage duration here. यहाँ पे zero voltage है, यहाँ पे zero voltage है, यहाँ पे zero voltage है. This is because of the inductive load. If you see the difference between the previous output voltage waveform and this output voltage waveform, that is of inductive and resistive load, in case of pure resistive load, this negative voltage was not there. As we have already seen in case of center type configuration, if the load is inductive, there will be negative voltage in the load, which indicates that the power is flowing from the load to the source. Actually, the power in this duration is negative because voltage is negative, current is positive. The product of positive into negative is negative. So the negative power indicates load is providing some energy to the source. यहाँ से energy यहाँ input side में जा रहा है. That is the indication of this negative voltage. Now we'll start with the working of this circuit diagram. Once this input voltage is applied to the circuit, during positive half cycle, SCR1 and SCR4 are forward biased because anode of SCR1 is at highest positive potential and cathode of SCR4 is at highest negative potential. And as they are forward biased and a gate pulse is applied at omega t is equal to alpha, this pair of SCR 1 and 4 starts conducting, and you will get the load voltage from alpha to this pi plus beta, right? And the voltage is positive from alpha to pi and negative from pi to pi plus beta. The voltage from alpha to pi is positive and from pi to pi plus beta it is negative because of the stored energy in the inductor. What happens at omega t is equal to pi, the voltage polarities are reversed. That means SCR1 and SCR4 are reverse biased, but when these pair of SCR were conducting, the inductor stores some energy, and the stored energy in the inductor will not allow this pair of SCRs, that is 1 and 4, to turn off. SCR1 और SCR4 को turn off नहीं होने देगा कौन? The stored energy in the inductor, because it has to release somewhere. So it will force these SCRs to remain in the on state, and the current flows through the devices SCR1 and SCR4 in the same direction. You can see here the current after pi. This is the current waveform, and at pi the voltage is reversed, but the current is flowing in the same direction. And up to what point this current will flow through the SCRs and load? Up to pi plus beta. यहाँ तक current flow होगा. During that duration, the energy stored in the inductor will be released to the source. It will go back to the source. Current is same direction, positive. The voltage is negative. This is because of the stored energy in the inductor. So you will get this negative voltage, and at omega t is equal to pi plus alpha. Omega t is equal to pi plus alpha. A trigger pulse to the pair of SCRs 2 and 3 is applied, and as these two SCRs, SCR2 and SCR3 are forward biased, they will start conducting, and from pi plus alpha to 2 pi will get the positive voltage across the load, and from 2 pi to 2 pi plus beta you will get the negative voltage across the load, and current will be from pi to 2 pi plus beta. It is flowing in the same direction. It is not going to change the direction. And at omega t is equal to 2 pi plus beta, as the voltage polarities across these two devices SCR2 and SCR3 is reversed, and the load current is 0 here at 2 pi plus beta, these two SCRs which we are conducting will turn off at 2 pi plus beta. Clear? At 2 pi plus beta, the pair of SCRs which we are conducting will turn off because the voltage polarities are reversed and the load current is, or the current flowing through the device is 0, and there is no current and no voltage. There is no voltage across the load from 2 pi plus beta to 2 pi plus alpha. Short duration है, लेकिन there is zero duration. From 2 pi plus beta to 2 pi plus alpha, there is no load voltage, there is no load current. So this circuit is actually called as discontinuous current mode. Why? Because the load current is not continuously flowing. The reason is the value of the inductor is very low. That's why it is called as discontinuous current conduction mode. And where is the discontinuous current? You can show here beta to alpha in positive half cycle, first positive half cycle, and in second that is negative half cycle from pi plus beta to pi plus alpha, and in next positive half cycle from 2 pi plus beta to 2 pi plus alpha there is a zero current. It is discontinuous current conduction mode. So is that clear? Is there any doubt in this circuit? Waveforms? हॅलो,
येस सर, समजलं.
समजलं ना? बाकीच्यांना पण समजलं असं समजतो मी. येस, ओके. तो हाँ, this is case of low inductor value, and if the value of the inductor is very large, you can see the waveforms. यहाँ पे हमने ये नहीं देखा waveforms of current through SCR1, current through SCR2, current through SCR3, current through SCR4. So during first positive half cycle, SCR1 and SCR4 are conducting. ये देखो यहाँ पे SCR3 and SCR2, that means they were previously conducting. So the current was flowing through SCR2 and SCR3. यहाँ पे zero duration दिख रहा है, कोई भी device conduct नहीं हो रहा है, so there is no current. And after this, SCR2 and SCR3 are conducting for 180 degrees. यहाँ पे zero duration और आगे फिर SCR1 and SCR4. See the difference between the waveforms. कौन से साइड में कौन सा वेवफॉर्म है, लेफ्ट में कौन सा है? Yes. On the left hand side, the circuit is single phase full wave fully controlled bridge configuration with RL load, and load is inductive very high value inductance. On the left hand side, the same circuit with low value inductance. Now first of all, let us see the difference between the output voltage. यहाँ पे जो left side में है with low inductance value, you can see there zero load voltage duration, and there is no zero load voltage duration on the voltage of large inductance load. And the current you can see here, load current is continuous, a straight line. यहाँ पे जीरो पे आ रहा है, फिर इंक्रीज हो रहा है, फिर डिक्रीज होके जीरो हो रहा है, फिर इंक्रीज हो रहा है, फिर डिक्रीज होके जीरो हो रहा है. So the current is discontinuous, current is continuous, and this is supply current. And currents flowing through the SCRs, here you can see there is zero gap, there is a gap, there is no current flowing. यहाँ पे देखो कंटिन्यूअस, यहाँ या तो SCR1 SCR4 कंडक्ट कर रहे, या तो SCR2 SCR3 कंडक्ट कर रहे. यहाँ पे एक समय ऐसा है जहाँ पे कोई भी SCR कंडक्ट नहीं कर रहा है. That is because of the value of the inductor. So here you can say it is a continuous current conduction mode because the value of the inductor is very large, and in the previous case, that is low inductance value, the operation is discontinuous current conduction mode. The circuit works in the same way, just current can be continuous or discontinuous depending on the value of the inductor. So if in question on this single phase full wave fully controlled bridge configuration with RL load, if they mentions the value of, assume that the value of the inductor is very low as compared to the resistance, then you need to draw this discontinuous current conduction mode. They are going to ask this discontinuous mode directly or indirectly. They may ask the load inductance is low value, one and same thing. क्वेश्चन ऐसे भी आ सकता है कि एक्सप्लेन द डिसकंटिन्यूअस करंट कंडक्शन मोड ऑफ आरएल लोड फ्री दिस सिंगल फेज कंट्रोल रेक्टिफायर. तो डिसकंटिन्यूअस करंट कंडक्शन मोड या फिर लो इंडक्टेंस, और कंटिन्यूअस करंट मोड या फिर हाई इंडक्टेंस. वन ऑफ द थिंग दे कैन आस्क, और सिंपली दे कैन आस्क एक्सप्लेन द single phase full wave fully controlled bridge configuration with RL load. They will not specify whether the inductance is large or this thing low. So you can assume that the value of the inductor is either low or high. Depending on your assumptions, you need to draw the waveforms. If you assume L is very, very less as compared to R, you have to draw this waveform. If you assume L is very, very large as compared to R, you need to draw these waveforms. And you need to explain why this zero duration is there in voltage and current. Along with all these waveforms and circuit diagrams, you need to write the output voltage equations also. The output voltage equation for this circuit is this way. You can derive the equation for the average output voltage. VDC is equal to 1 by pi integration from alpha to pi plus alpha. We are assuming a continuous current conduction mode. So you need to show this alpha to pi plus alpha. अगर डिसकंटिन्यूस करंट रहता तो अल्फा टू पाई प्लस बीटा था, राइट। कंटिन्यूस में अल्फा टू पाई प्लस अल्फा रहेगा Vs और Vm साइन ओमेगा टी डी ओमेगा टी। Vs is the source voltage. Source voltage क्या है? Vm sin omega t d omega t. And if you simplify these, you will get this voltage. Vdc is equal to 2Vm by pi into cos alpha. This is the average output voltage for the single phase full wave fully controlled bridge configuration with RL load. Clear? Previous case में कैसा था? With pure resistive load, what was the equation for the output voltage? It is Vm by pi into 1 plus cos alpha. अभी टाइम कम है, हम नेक्स्ट क्लास में कंटिन्यू करेंगे. जस्ट आई विल टेक द अटेंडेंस. शुभम माळे and 2 more joined. क्लासला सौरभ नायकोडी. ठीक आहे.
ओके सर.
ओके बाय.
बाय सर.
बाय.